Testing 1, 2, 3, 4. Can you hear me?
Loud and clear, doctor.
Can hear, doctor.
Thank you. Waiting for others to join. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullah. Good afternoon, everybody. How are you guys? Okay.
Alhamdulillah.
Okay, so we continue our lecture from last 2 days regarding the frequency response and the stability analysis. Okay, so frequency response, we are using a graphical approach, namely known as boat plot. Okay, which consists of 2 plot. One is magnitude in decibel versus frequency, and the other one is phase in degrees versus frequency. So the frequency scale is using a log scale, okay, a logarithmic scale. Okay, and then we also look at the several factors of workload, okay, including the gain factor, the derivative S factor, the integral 1/S factor, zeros at the real axis, poles at the real axis, complex conjugate poles second order, and complex conjugate zeros second order. And then we move to the stability analysis, okay, of the workload using a frequency response technique. So I discussed already with you that we have 3 situations, which is stable, unstable, and marginal or critical. So stable when the system, okay, has a gain margin and phase margin at positive value, positive dB and positive degrees. So that system is considered as a stable system. And then we also look at the unstable system, where unstable system will give us negative gain margin and negative phase margin. Okay.
Sorry, doctor, are you sharing your screen? I can't see your screen.
Yeah, just the introduction.
Okay. Okay, sorry.
Okay. Then we also look at the marginal condition or critical conditions. Okay, where the gain margin and will give you 0 decibel value, and phase margin will give you a 0 degrees value. Okay, and when it's critical, the indicator is the omega gain margin is equal to the omega phase margin. The frequency gain margin equal to the frequency phase margin. Now I will share with you, okay, the slides. Okay. Okay, can you see my slides, guys?
Yes.
Right. So this is what I'm talking about. Okay. We have a gain margin and phase margin concept. So I hope everybody please digest this. Okay. Very important, very significant. Okay. So gain margin, okay, is over here, right? Okay. Gain margin is over here, where this one, okay, it occurs at omega GM, okay, gain margin frequency, and this point is when the phase curve cross minus 180 degrees. Okay, so it will give you omega GM, gain margin frequency, and gain margin frequency will give you the gap, okay, between the curve value, magnitude value, and the 0 dB. And then the phase margin, okay, phase margin is over here. Okay, phase margin occurred at this frequency known as omega PM or omega psi M. Both are same. So I usually use omega PM. So omega PM occurred when the curve, magnitude curve, cross 0 dB line. Okay, so this is a 0 dB line. Okay, so it will give you a gap which is known as the phase margin. So last 2 days also I discussed with you the example 4, okay, and I show you how to get to obtain the gain margin and the phase margin. And this one, this data is based on the straight line approximation. And the one that I show in the Matlab is actual or real data plot. Okay. So the difference is you will get a different answer, but not far away between each other, which is acceptable. Okay. So this is the plot that we get using a Matlab. You can see that when you play around the magnitude curve and the frequency curve, okay, using your mouse, so you can scan the values at 0 dB and minus 180, which will give you the omega phase margin and omega gain margin, and from there you will get the phase margin and gain margin. Okay, so this one is from the Matlab. Okay, as I showed you before. So the gain margin is positive. Okay, positive 5.53, and this is the omega GM phase margin, and the phase margin is also positive, which will give you the omega PM, omega phase margin. Okay, so system is stable. Right, so this one is similar about this one, but it just gives you the value of the frequency, 4.5 and 6.21 radian per second. So from the final booklet, the gain margin is positive 5.53 decibel. The omega GM, okay, gain crossover frequency, okay, at minus 180 degrees is 6.16 radian per second. Phase margin is 23.5 degrees, which will give you the omega PM phase margin at 4.51. So system is stable, okay, due to the positive value of gain margin and phase margin. So prepare a board diagram for the open loop transfer function below. Okay. So in this case, the original one is GS is equal to 5 S 1 plus 0.6S multiply 1 plus 0.1S. Okay. Determine the phase margin, gain margin, gain and phase over crossover frequency when the system is stable, unstable, and critical. So we have to play around. Kita nak ubah apa? What we're going to vary, okay, to make the system stable, unstable, and critical. So we have to vary this value, the gain, okay, the gain K. So in practical, we are using potentiometer, okay, we not output and input. So from here, we can adjust the gain 5, 50, 500, 100, and so on by turning the knob of the potentiometer. Right. So the calculation for the gain in decibel is carried out using the formula 20 log G, which is the open loop transfer function. 20 log 5 minus 20 log omega minus 20 log 1 plus 0.6 j omega minus 20 log 1 plus j 0.1 j omega. Okay, which will give you the data for the dB with different frequency value. But for constant, 20 log 5 is 14 decibels. Similarly, for the phase calculations is shown here as well. For constant, okay, is minus 90 degrees, minus arctangent 0.9 omega. So this one is sorry, this is not constant. This is for the 1 over S. Okay, and this one is 0.6 omega arctangent and 0.1 omega arctangent, which will give you the data for the phase in degree. Okay, so as we are using a Matlab, okay, so we can generate this, okay, using a what do you call that, a Matlab. So I think I share with you. Okay, can you see the Matlab in your screen?
Yes, Doctor.
Okay. So S is equal to transfer function S plus the P. G is equal to 5 divided by S multiply 1 plus 0.6 multiplied by S multiply 1 plus 0.1 multiplied by S. Okay. So we have a syntax error. So where is the problem? Okay. I know. So I have to change this one. Double. Okay. This one. Okay, this one must be okay, right? There you go. Okay, and then both G. So it's busy calculating now. Okay, so just come out. Okay. So share. Can you see?
Yes, Doctor.
Yes, Doctor.
So we put the grid, logarithmic scale, okay, and then find the characteristic, which is the minimum stability margins. There you go. So from your observations, is it the system is stable, unstable, or marginal? We have to scan. Okay, so you have to click this blue line, blue dot. Okay. Okay. Oops. So he will give you 7.36 decibel and 18 degrees positive. So the system is stable. Okay. The system is stable. So may I ask Nur Aina Shafika? Nur Aina Shafika?
Yes, doctor.
What is the value of omega GM, gain margin frequency?
2.61 radian per second.
I'm afraid your answer is wrong. The answer is 4.08 radian per second. The one that you mentioned is
They are.
mata salah tengok.
I see. Okay.
Take note, please. Right. So from the final workload, we observe that the gain margin is 7.36 decibel at omega GM 4.08, and then the phase margin is 18 degrees positive at omega phase margin 2.61 radian per second. Okay. Overall, the system is stable due to the positive value of the gain margin and phase margin. Right. Now we change. We go back to the our double prong Matlab. Okay. Right. Which is here. Okay. Okay. So we change from 5 to 50. Okay. So we adjust the potentiometer. Okay, adjust the potentiometer. So make it 50. Okay, then board. All right. Where is the plot? Okay. Okay. Put the grid. And then put the characteristics, minimum stability margins for all. Okay, now we click this value. And then this value. Okay. Yosef? Yosef?
Yes, doctor.
What is the gain margin value?
The gain margin minus 12.6.
What is the omega GM gain margin frequency?
4.08.
Ala Akhi Ala sleeping. Alicia Zaidi? Alicia
Yes,
Zaidi?
doctor.
What is the phase margin value?
Negative 26.8 degree.
Okay, what is the phase margin frequency?
7.98 radian per second.
So what is the conclusion of stability?
Unstable. Stable.
What did I tell you just now?
Stable.
Stable, unstable. The system is unstable due to negative gain margin and negative phase margin. Alicia,
Yes, Doctor.
please take note.
Okay.
All right, thank you. Now we change 50, we reduce back. Okay, we reduce back to 11.75. Okay, so 11.75. Can you see? 11.75. Okay. Good. Okay, get the plot. Okay, so Azira Ahmad.
Okay.
Azira,
Yes.
what is
Yeah,
the value of gain margin?
Minus 0.0618.
Okay. What is the gain margin frequency?
4.008 radian per second.
Nur Izzah Hakimah.
Yes, doctor.
What is the phase margin value?
Negative 0.143 degrees.
What is the phase margin frequency?
4.1 radian per second.
What is the conclusion for the stability?
Unstable.
Unstable. It's marginal. Okay.
No margin.
4.1 and 4.08 is near, so it's almost the same. This one almost 0 dB and 0 degree. So more or less kosong lah, kosong degree and 0 degrees and 0 decibels.
Doctor?
Yep.
I know that the system will be stable when the gain margin and phase margin are both positive. But what happens? Is it possible if the gain margin is positive and the phase margin is negative, or
It's
vice
not-
versa?
Not possible.
Not possible.
Not possible. Not
All right.
possible, Telper.
Thank you, Doctor.
All right. Any questions?
Sir, what's the threshold of it being 0? Because if you look at the phase margin, it's not actually 0.
Okay.
But at what point does it become 0? If it's 0.5, is it still 0?
Well, we have to tune the gain. Okay, the one that I do just now is 11.75.
Yes.
Let's say we increase it to maybe 11.7. Okay, so you have to play with that. Okay, 11.6 perhaps. Oh, okay, 11.6. Okay, change to 11.75 to 11.7. Okay, because when we tune very high, it's unstable, so we reduce it to 11.7. Okay, and see what happens. Okay, all right. Actually, there is no threshold. Actually, you have to play around with the gain. Okay. Okay. Right. So now this is 11.7. Previously 11.75, kan?
Yes.
Okay. Put the minimum stability margin. Okay. So you can see that the position of this blue line at the magnitude curve and the frequency curve is almost the same. So minus 0.0248, minus 0.0572 degrees.
That's obviously 0 lah.
Well, obviously 0 lah. Kalau you round up, you go to the pump station, they won't count lah. 1 cent or 2 cents. Halal lah, halal and taibah.
True.
Okay. So I think the critical might be 11.7, 11.65. Okay, let's say we go to 11.6. Why not? Why don't we try to 11.6? Okay. Go here.
But my question was if it landed on 0.5 instead of 0.000. So do we treat that as 0?
Yes, you can treat it as a 0, no problem. So 11.6. 11.6. Shall we? Okay, 11.6. Okay, change to 11.6. Okay, so we go to the board. Okay. Okay, again, you see that still the same, very near each other. 0.0498 positive now. It's positive now. And the phase margin is 0.115. It's positive. Previously, 11.7 is negative, positive. When you go to 11.6, so in between is 11.65. You have to play around. Play around. Go to the 11.65. 11.65. Okay. Then good. Okay, you don't have to type. You just press the arrow up and down. So the command is there. You can edit straight away. Okay.
Thank you, Doctor.
See, I think this one almost 0. 0.0124 and phase margin 0.0287. So 0.0. So okay lah. Okay, 11.65 or 11.6 should be okay. Just to show you the marginal stable conditions. Start mirroring. Okay, ada soalan? Any question? Rahi? Alright, brothers. Any soalan? Any question? No questions. Okay, if no question, we move to the next subtopic, which is the relation between closed loop time and closed loop frequency response. So there is a relationship between closed loop and closed loop time and closed loop frequency response. Okay, time domain and F domain. Okay, so by considering the second order feedback control system, which is here, this is the open loop. So when you apply closed loop, it will go to here, which is omega n square divided by s square plus 2 zeta omega ns plus omega n square. So you simplify it. Okay, you simplify, and then you will get m magnitude. Okay, and these expressions. Then you plot the magnitude log. Okay, for the closed loop frequency response. So you will obtain this blue line. Okay, this blue line. Okay, which is starting from 0, it goes up with the peak magnitude, MP, magnitude peak, and at the peak frequency, omega p. Okay, and at minus 3 dB, here is the minus 3 dB, is the bandwidth. Okay, the bandwidth frequency. So what I'm going to tell you, okay, for closed loop frequency response, you will get 3 informations. 3 important information. First is the peak magnitude. Second is the peak frequency. And third is the bandwidth frequency. at minus 3 decibel. Can you please remember this? Closed loop frequency response, you will get 3 info. First one is the peak magnitude in decibel. The second one is the peak frequency in radian per second. And the third one is omega bandwidth, the bandwidth frequency in radian per second at minus 3 decibel. Okay. Previously, in open loop frequency response, you will obtain 5 info. Am I right? First is the gain margin. Second is the phase margin. Third is the omega GM. Fourth is the omega phase margin and stability status. Stable or not stable or marginal. So everybody please remember, for closed loop frequency response, we will obtain 3 important information: magnitude peak, peak frequency, and bandwidth frequency at minus 3 dB. For open loop frequency response, you will obtain 5 important information, which is the gain margin, phase margin, omega GM, omega PM, and stability status. So the magnitude peak is represented by this formula, 1/2 zeta square root 1 minus zeta square. And the peak frequency is represented by omega P, omega N, 1 minus 2 zeta square. Okay. So when you obtain the MP, which is 15 decibel, so you want to change to the value of MP without dB, so you have to use the anti-log. Okay, so this is anti-log, which is 10, 15 divided by 20. So you will get the 5.234, okay, which is the MP, not in dB lah. But of course, if you want MP in dB, so you have to 20 log 5.6234. So we will get 15 decibel. So this one is the same, one in dB, one in without dB. So if you want the MP without dB, so you have to apply anti-log, which is 10, 15 divided by 20. Understand? Guys?
So far, so good.
Okay. So 3 important information, as I told you before, I repeat again, you will obtain MP, you will obtain omega P, and you will obtain bandwidth. So bandwidth, you have to search the minus 3 dB, go to the line until it intersection with the magnitude curve and go down. So you will get the omega bandwidth. Relationship between the closed loop time and closed loop frequency response. So therefore, the maximum magnitude is directly related to the damping ratio and overshoots. We have a standard curve, okay, which is MP versus overshoot. Okay, so this curve is standard, will be attached to the test and exam if needed. Okay, so for example, this one is MP is about 4.4, okay, which will give you the overshoot percentage is about 68%. Okay. So relationship between closed loop time and closed loop frequency response on the bandwidth is the frequency at which the magnitude response curve is minus 3 decibel. Okay. So if you go to the any electrical appliance, especially the audio, okay, you can check the spec design. What is the frequency at minus 3 dB? Okay. So the relationship is shown here. Okay, between the bandwidth and the time response specification, which is omega bandwidth in terms of omega n and zeta, omega bandwidth in terms of TS, omega bandwidth in terms of TP. Okay, so they have 3 formulas, and the graph is shown here. Okay, at minus 3B, which will give you the omega bandwidth. For example, So consider the unity feedback system with an open loop transfer function, which is GS 1 over S 1 plus S 1 plus 0.5S. Okay. Determine the gain margin, phase margin, omega GM, PM, and system stability. Fine, no problem. Okay. Determine the magnitude peak, MP, peak frequency, omega P, and bandwidth using the closed loop. So this one is open loop transfer function. So the closed loop will be Ali Imran 1 over
1 over S 1 plus S 1 minus 0.5S plus 1.
mana ada minus.
Eh.
Kan? This is what you mentioned.
Yes.
Okay, so now we go to the Matlab. Oh, panas pula. So go to the Matlab. So now we have two conditions. One is the open loop, the other one is the closed loop, right? Two different plots. Okay, so we type G first, the open loop. 1 over S plus multiply S plus 1 multiply 1 over 0.5 multiply S. Okay, close bracket. So this is open loop. So directly both to G. Okay. So we get the plot now. Okay. Everybody, can you see the plot?
Yes.
Okay. So this is open loop, huh? Open loop. Telpel. Telpel Gil.
Maybe goes to the toilet.
Okay. This guy always go to the toilet. Lukman Hakim. Lukman. Lukman. Tidur. Liana.
Yes, Doctor.
What is the gain margin?
9.54 dB.
dB. What is the omega GM?
1.41 radian per second.
What is the phase margin?
32.6 degree.
What is the omega phase margin?
0.749 radian per second.
What is the system stability status?
Stable.
Why?
Because GM and gain margin and phase is positive.
Phase margin is positive. Excellent. Thank you very much. So we go to the closed loop now. Okay, guys, we go to the closed loop. Okay, so closed loop is different. So we have to use a GCL lah, G closed loop. Okay, so I make it a difference from the open loop. So it's equal to 1 divided by S multiply S plus 1 multiply 1 plus 0.5 multiplied by S, okay, plus 1. Okay. So this is closed loop. Okay, so both GCL closed loop. Okay, I share the screen, the plot. You can see the plot is different. Okay, from the open loop.
No plots.
New plot. Can you
Okay.
see?
Now I can see.
Okay. So now we have to use the peak response, because in open loop, peak response doesn't mean anything to us. No info. Okay. So we have to click at the peak response there. And then we have to go to the margin, no need, because margin, stability margin, and all are relate to the open loop, right? So now we click here. Apa nak tanya? Abdul Rahman. Abdul Rahman. Abdul Rahman. What is the magnitude peak in decibel?
5.28 dB.
5.28 dB. What is the peak frequency?
0.824
Radian.
radian per second.
What is the magnitude peak without dB?
Aduh, nak kena kira pula.
Siapa pandai? 10, 5.28 divide by 20. How much? Anti-lock.
1.837.
1.837.
837.
Betul eh? Okay.
Yeah.
Okay. And what is the bandwidth frequency? Bandwidth frequency. Man.
10 power 4.
10 power 4. Astagfirullahaladzim. Tak tahu, tak tahu. Scan lah. Klik di sini. Klik. Then you scan. Minus 3 dB. Stop kat saya. Minus 3 dB. Sekarang minus 7. Minus 3. Nampak tak? Can you see?
Oh.
Yeah. Can you see? Minus 3 dB. Jap. Di tangan bagi stretching sikit. Okay. Okay. Then it goes. Oops.
Sikit lagi.
Susah.
Fine tune.
Fine tune lah. Itulah. Tangan jangan gigil. Tangan jangan gigil. Jaga pernafasan. Okay.
Okay, that's close enough.
Boleh lah. Okay. Lebih kurang lah. Minus 3 decibel. Which is 1.27 radian per second. Lukman, faham tak? Man.
Faham, Doktor, faham.
Scan pakai mouse.
Okay.
Scan pakai mouse. So we go back to our slides. Okay. Okay. So we already plot. Okay, we obtain the answers stable. Okay. Then we obtain the closed loop. Okay, just now. Okay. The 20 log M, 5.28 decibel from the graph. Then I asked Lukman, what is the value of MP without decibels? So we're using anti-lock. 10 power of 5.28 divided by 20. Then we obtain 1.8365. Then the peak is at MP, peak frequency 0.824 radian per second, and at minus 3 dB, then we scan using our mouse. Okay, then we obtain minus 3 dB at the bandwidth 1.26 radian per second. Boleh? Can you digest this? Can?
Can.
Okay. Okay, guys, we stop here. Next example, we will go, inshallah, next week. Inshallah. Any questions? Any question to ask?
Do we have to do this in line approximation? Close loop code block.
Well, sometimes, okay, but in tests and exams, the plot are given. Okay, the plot are given properly. They draw the word plot using Excel. Okay, and then they attach at the test and exam questions. Okay, including quiz, which will be held on the 5th of May. Okay, at 9:30.
We don't have to.
No need to plot.
No need to plot anything, right?
No need to plot. Maybe they will ask to sketch freehand draw. That's all. For example, draw freehand draw for open loop transfer function 10 over s plus 2. I think you know how to plot using a sketch. Simple one lah. First order. Any question, guys? All right, brothers. Okay. Only 23 attendance today, mashallah.
Thank you, Doctor.
Ahmad Abulita.
Yes, Doctor.
Anta Fahimta.
Yes.
Abdul Ghani.
Doctor, what about the quiz? You said that it's on the 5th at 9:30.
You have a cam, isn't it? You have a cam.
Yeah. So some of us have
five or six students. 6 students involved in the camping. I don't know what camping is it during Ramadan and during pandemic. What is this? Who? Oh, it's not a camping. It's a test. Sorry. It's a test. Okay.
Artificial
AI
intelligence.
test, yeah. Artificial intelligence.
So they will give you another quiz. Another quiz.
Right.
Another quiz. I will update you the time and the date. Okay. So for at the moment you can focus on the test one and a half hours. Artificial intelligence. This is SKEM student. SKEM.
Yeah.
Okay.
What are you doing here in ski class?
Scam student. SKEM.
Yeah.
The rest okay. No problem. Okay. There is a repeat session. The question is there. It's random. Ni Umar question and Nur Aina Shafika is not the same question for quiz. They are randomly. I don't know how e-learning randomized. So you will get a different question. You cannot communicate each other. Okay. All right, guys. Okay. Thank you very much to join. Okay. Have a nice weekend. See you next week, inshallah. Assalamualaikum.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much.